Swayam Prabha. Digital India. Educated India.
Now we are going to introduce the concept of faster least square solution, faster least square approximation using randomized approach. This aspect of the theory of randomized algorithm is very well understood. I am going to give you a glimpse of the results in this area. This area is still very active. Area of research is hardly 25 years old. So, there are lots of good questions to ask as well as experimental projects one can generate out of this. So, faster least square approximation. Let n be an integer, square bracket within, if I embed n within the square bracket as we have done, it represents a set. So, it is a shortened form of the set of natural numbers from 1 through n. We just finished the Hadamard matrix, that is the reason why we did Hadamard matrix, which is also called Hadamard transform. Hn is defined recursively. You already know H2 is 1 1 1 minus 1, Hn is Hn by 2, Hn by 2, Hn by 2 minus Hn by 2. So, without the constant 1 over square root of n, it is called the Hadamard matrix. If I multiply by a constant, it is called normalized version. Here n is a power of 2, that means the size of the matrix increases as powers of 2. If you did not divide by the normalizing constant 1 over n, the matrix will be orthogonal. That means, if I picked any two columns, which are any two distinct columns, they will be orthogonal, but the square of the inner product of a column with itself will not be unity, it will be n. Therefore, if you divide by square root of n each of these matrices, matrix of size Hn at nth order Hadamard matrix, you get orthogonal matrices. That means the inner product of a column vector with itself will be unity. Now, I am going to introduce another matrix. D is a diagonal matrix, D11, D12, D, and then there are n diagonal elements as a square matrix. I am going to pick the ith diagonal element of this square matrix to be is equal to plus or minus 1 with a probability half-half. So, H is not random, H is defined recursively, is a deterministic matrix. I want to introduce some randomness into H, and to that end I am going to design a new matrix called diagonal matrix, whose elements are plus or minus 1, and each diagonal element is going to be obtained by flipping a coin plus 1 or minus 1 with a probability half-half. So, DH. So, what is DH? If you multiply a matrix by a diagonal matrix on the right, the ith diagonal elements is going to multiply the ith column. If you multiply a matrix by a diagonal element on the left, the ith diagonal element is going to multiply the ith row. So, what is that? Now, D multiplies H on the left. So, if it is H on the left, it is the DII multiplies the ith row. I could have as well multiplied H by D on the right, it will multiply the column. So, what is the idea here? Multiplying H by this diagonal matrix whose entries are random tries to make that product random. So, that is called randomized Hadamard transform. So, Hadamard matrices, normalization, Hadamard matrix inherits the fundamental property of orthogonality, symmetry and involutive nature. Now, I am trying to go one more step. I am going to multiply Hadamard matrix either on the left or on the right by a diagonal matrix whose entries are plus or minus 1 with a probability half-half. So, multiplying a Hadamard matrix by a diagonal matrix either on the left or on the right is going to randomize, and is called randomized Hadamard transform. So, two of the properties of DH. First property we have already seen, the matrix vector product DH x. Now, please understand, DH inherits all the properties of D except that is random. It can be computed in n log n time. So, you can compute Hx in n log n time, and then you can multiply the vector Hx by D. Multiplying a vector by a diagonal matrix involves only n operations. So, multiplying the vector Hx by D tries to randomize the components by multiplying it plus 1 minus 1 with a half-half probability. Now, please understand, Hx can be computed in a log n time by the standard fast Fourier transform methods. I already told you H plays the role of Fourier transform in real domain. So, you can think of DH as trying to compute the Fourier Walsh transform, Hadamard 4 Walsh transform in a log n time. So, that is one property that we have already seen, and is the consequence of the properties of H, and we saw in the diagram that there are log n stages, and each stage there are n operations, so n log n. There is another fundamental property whose proof I am not going to go into the details right now, but it is much more fundamental, equally fundamental, just like the computational advantage. So, there is a vector x, then there is a vector y. Y is the transformation of the vector x. There is a fundamental property in Fourier transform which you should know if you have done some signal analysis. The Fourier transform of a delta function has energy in all the frequency components. I hope you understand that. That means delta function is very peaked. So, if the signal in the time domain is very peaked, that means the energy is concentrated on only one time. When you consider it in the Fourier transform, in the transform domain the energy gets distributed to all the frequencies. One of the implications of that is that the vector and its Fourier transform both cannot simultaneously have energy concentrated in a small subdomain. So, if the time domain signal is concentrated, the frequency domain signal will be spread, and vice versa. So, when DH is applied to a vector x, it spreads the energy. That is the idea here. It spreads the energy in the delta function to all the frequencies. This ability to spread the energy across after you transform that is a fundamental property that we are going to exploit. And I have already introduced you to the infinity norm. What is infinity norm? Infinity norm is the maximum of the absolute value of the components of vector x. So, by applying HD to x, if I can show the energy in the resulting vector spread out means what? The maximum absolute value of the components of the transformed vector is bounded above. That means when applied to a vector, it spreads the energy in the vector in the sense that x infinity norm is bounded after the application of dH. So, if x has unbounded or large x infinity norm, once you apply dH to x, and if you compute the infinity norm of the resulting vector has a bounded infinity norm, and this essentially comes out of the spreading property. Where are we going to exploit the spreading property? You remember when we talked about sampling, random sampling, if the columns of a matrix A are such that if the square of the column, if the energy in the column as measured by the square of the Euclidean norm of the columns are very different, those columns whose energy is larger are going to dominate, and those columns whose energy is smaller, they are not going to be as dominant. So, it is this distribution of the energy across the rows and across the columns that was exploited to the benefit of designing random sampling based algorithm in randomized linear algebra. So, by applying HD to the vector x, if I can spread it out, then what does it imply? The norms of the columns of A, the norms of the rows of A are not going to be too different, they are going to be very nearly spread out, and they are all going to be bounded, and there is not much of a difference between the energy in various columns or rows. In that case, I do not have to use importance sampling based on the square of the length of the column or rows. I can simply use uniform distribution. That means I am going to have to save, I will be able to save money in computing the probabilities that are proportional to the square of the length of the, or the total amount of energy in the columns and rows of A. So, that is another important consequence. So, by applying the Hadamard transform, I am trying to equalize the energy. I am also going to benefit in terms of the computational advantage of reducing n squared to n log n. So, it is a win-win situation. So, by applying the Hadamard transform, we are going to gain in two directions, as we just talked about. Also remember, again I want to emphasize, in computing dH there is no multiplication involved. So, let us see where we are. I introduced Hadamard transform per se. I introduced the notion of involutive operators. I gave examples of functions that are involutive. We gave examples of orthogonal matrices that are involutive, orthogonal matrices that are not involutive. We are trying to understand this notion of orthogonal symmetric involutive operators called the Hadamard transform, normalized and unnormalized version. Then we introduced the notion of a randomness by multiplying it by a diagonal matrix with the diagonal elements being plus or minus 1, equally likely with a probability half-half. And we saw the advantage of it. One is computational, another is the ability to spread the energy. With these tools on hand, now I would like to come back to visit one of the problems in linear algebra. Please understand, there are several problems in linear algebra, but what are the major bulk of the computations that are done in applied science and engineering? Solving Ax is equal to b when A is a square matrix non-singular, solving a least square problem, solving eigenvalue problem, and variances thereof. So, let us consider the classical least square problem. I am changing the symbols. A is m by n. I used to say h is m by n. I used to say z is Rm. Now, in the case m is greater than n, and I am assuming A is full rank. So, I want to be able to solve Ax is equal to b. When m is greater than n, A is full rank, we already know how to solve it. Moore-Penrose inverse. So our goal is to find x such that minimize Ax minus b, square of the norm of Ax minus b, the residual with respect to x is an unconstrained minimization. Let the minimum value of this residual be z. Please understand, this is the optimal value which I know how to calculate. And the minimizer XLS is given by A transpose A inverse A transpose B, which is A plus B, A plus A to the A plus refers to the generalized inverse of A. When A is a full rank, the generalized inverse is given by A transpose A inverse A transpose. So that's the least square problem we already know. I already know how to calculate XLS in 4. I also know how to calculate the minimum value of the residual, minimum value of the square of the residual, which is essentially the sum of square residuals. Now, in trying to solve this least square problem in a randomized fashion, I am going to introduce the notion of what is called a preconditioning matrix B. Let B be a R by M matrix, where R is much less than M. What is M? M is the number of rows of A. What is N? N is the number of columns of A. What is R? R is the number of rows of B, the preconditioning matrix. So, when I multiply A by B, I am going to get an R by N matrix. R by N matrix has a smaller dimension, smaller row dimension compared to A. So, now I have Ax minus B, I am going to multiply Ax minus B, the residual, by B. Now, please understand, I have called sometimes Z minus Hx residual, here I am calling Ax minus B residual. Now, please understand, when I am doing the square, this is the same as the square of the norm of B minus Ax. So, there is nothing unusual about these symbols, I am using the same notion of the residual. So, multiplying this least square problem both sides by B is called preconditioning. So, if B is an identity matrix, I am not changing anything. If B is a matrix with less number of rows, I am trying to reduce the dimension. If I am going to reduce the dimension of the problem, what are the consequences? Why do you do that? And how do you get it done? And how do you approximate the solution to the least square problem? We already know the exact solution, which is 3. So, let Z tilde be the solution such that it minimizes B times Ax minus B, the square of the norm of that, which is the equation 5. Now, assuming BA is a matrix of full rank, I can compute Z tilde is the result of X tilde LS, which is BA in generalized inverse times BB, and BA, the generalized BA plus the generalized inverse is given by the right hand side of the equation 6, which you already know. So, we can find the least square solution either by solving the linear system or by using sequential minimization such as Gauss gradient method. So, I am not going to tell you how to find X tilde XLFS. It can be found by solving the normal equation or by directly minimizing the objective function using sequential minimization such as conjugate gradient method, which we have already seen. So, you can see the power of what we have covered thus far. This operator, the preconditioning matrix in the literature, is also called downscaling operator. Why downscaling? I am trying to reduce the number of rows of A. Now, I am coming to the choice of B. So, what kind of matrix is B that can help you to solve the least square problem using randomized algorithm? Now, please understand, I am trying to apply the randomization in here not because I do not know how to solve it, but because I would like to be able to approximate the solution to the least square problem when the problem size is very large quickly. So, can I get a fast but approximate solution to this least square problem by downscaling, by multiplying both sides by with a matrix B, which is called the downscaling matrix. B has less number of rows than A. There are two choices again. So, randomized algorithm for solving least square problem reduces to selection of this downscaling matrix B. Once I fix the matrix B, I do know how to solve the problem in the previous page. Please understand, equation 6 and equation 5 together define the solution to the rescaled version, and we also know numerical methods for solving that. So, the whole responsibility of implementing this idea rests on the choice of B. Now, please recall, there are two ways of attacking the randomized algorithm. One is called random sampling, another is called random projection. I have introduced uniform sampling, I have introduced important sampling. Uniform sampling picks a set of numbers from 1 through n with equally likely. Important sampling is going to pick the columns based on the distribution of energy across the column space. Random projection is equivalent to designing a randomized projection matrix R and multiplying it. Now, you can see all the things that we have seen in randomized linear algebra now come to our help to solve the least square problem faster. So, there are two approaches, random sampling approach. In random sampling approach, how do I design B? B is designed as a product of S transpose HD. HD is our old friend. DH HD, you can see there is a symmetry, right? I can multiply, I can randomize H either by multiplying on the left or I can multiply on the right, which we have already discussed that. So, S is a new matrix. S is called the sampling matrix. HD is called the randomized Hadamard transform. So, by combining the randomized Hadamard transform and the random sampling methodology. Now, random sampling earlier depends on the important sampling, but if I multiply a vector by HD, the energy in HD is distributed across and spreads out. If it spreads out, there is no need for important sampling. So, sampling could as well be a uniform sampling. In the random projection method, on the other hand, I am going to express B as the product of T times HD. HD again the randomized Hadamard transform. T is the random projection matrix. Please understand, the random projection matrix can be of type 1, type 2, type 3. We have already talked about that, right? In type 1, the elements are plus or minus 1. I am sorry, in type 1, there are elements, the elements of R are from IID normal distribution, standard normal. In type 2, they are plus or minus 1 with probability half-half. In type 3, 66% of the time it is 0, the rest of the time it is either plus 1 over square root of 3 or minus 1 over plus square root of 3 minus 1 over minus square root of 3. So, the third type is essentially a sparse type. Third type involves multiplication by much smaller number of much smaller number of non-zero elements. So, you multiply only 1/3 of the time, 2/3 of the time I am multiplying by 0 in the third type. In type 2, there is no multiplication, it is only addition subtraction. In type 1, there is multiplication and addition because the random number Rij are going to be Gaussian distributed, they are real, they could be positive, negative. So, computationally type 2 and type 3 are much cheaper. Computationally type 2 and type 3 are much cheaper. I am bringing in further cheapness into the computation by bringing in Hadamard transform, because Hadamard transform can be operated in n log n steps. So, you can see how so many different ideas come to coalesce. So, depending on which path I want to walk, I can design B. So, B is a common matrix. designed in one of two ways, based on the random sampling, based on the randomized random projection. I have already talked about the choice of random projection at great length. So, implementing B as T times HD in the equation 8 is rather straightforward. Implementing B as S transpose HD is also straightforward, but instead of using the important sampling, I am going to use a uniform sampling. So, for completeness, since we have not used uniform sampling in our algorithm, even though that is possible, I am now going to spend few minutes on the choice of S, the sampling matrix S. So, what is the only thing that differentiate B on equation 8 and 7 and 8 is either you multiply HD by S transpose or you multiply HD on the left by T. T we already know, so S also we know. For completeness, I am now going to describe the properties of S. How do I fix it? So, let S be an M by R matrix. That means S transpose will be R by M matrix. Initially, this matrix is empty. Initially, this matrix is empty. So, R is a parameter which I am going to decide. So, for T, there is a loop for T 1 to R, select uniformly at random integer from 1 to n. So, look at the notation now. Square bracket n means there is a set of numbers from 1 through n. So, I am now going to select uniformly. This is the major departure. In the selection based method, we have seen that unless you use important sampling, selection based method will not be efficient in the sense of reducing the variance of the estimates, and that is what we illustrated in matrix vector product, matrix product, and sketch of a matrix, and so on. So, I am going to generate from the integers 1 to n an integer I that is uniformly distributed with a probability 1 over n 1 over n. If I picked I am going to create a vector. EI is the ith unit vector which is a standard ith unit vector which is 1 and the ith location, 0 elsewhere. I am going to multiply by a scaling factor m over square root of m over r, square root of m over r. That is simply a scaling factor to be able to achieve what we want. So, EI is now added to the matrix S as the ith column. Originally, the matrix S has m rows and r columns all are 0, empty. Empty means zeroed out. Initially, I pick an integer I with a probability 1 over n in the interval 0 to in the interval 1 to n. So, if I is picked, I am going to create a vector which is EI scaled by square root of m by r and attach this vector as the ith column of the matrix S. You repeat this r times. I am now at the end of this loop, I am going to get a matrix which is m by r. This m by r matrix whose transpose is used in 7 S transpose HD. So, if you used this preconditioning matrix, what is the claim? Instead of solving Ax is equal to B, I will now solve Bax is equal to capital B times smaller b. The claim is this computation can be done very fast because r is smaller than m. On the other hand, if I want to go the random projection way, T is Tij. I already talked about this. Tij is IID normal, Tij is plus 1 minus 1, Tij is plus or minus square root of 3 0. The Tij is 0 with the probability 2/3, it is going to be equal to plus or minus square root of 3 1 over 6. If I did this, what is that I am going to achieve? That is a lot of mathematical details involved, but I am going to give you the claim. Claim is kind of a theorem. So, instead of calling it a theorem, I am calling it a claim. So, what is the theorem? Let A be M by M matrix, B is the M vector, epsilon be a number in between 0 and 1. Then there exists a randomized algorithm. A randomized algorithm, either the selection type or the random projection type. Please understand, the proof follows very similar lines. There exists a randomized algorithm that returns the vector x tilde optimum such that x tilde optimum is the one. When I substitute x tilde optimum, what is this? This is the norm of the optimal residual. X tilde optimum is the approximating solution to the preconditioned version of the problem. I am trying to solve the preconditioned version of the problem optimally. X tilde optimum is essentially the solution to this preconditioned problem. Z, you remember we talked about, that is the minimum residual by solving it optimally without preconditioning. So, the minimum residual in the approximate problem is no more than 1 plus epsilon times the minimum residual in the optimal case. That means, if you took the ratio of the minimum residual in the approximation to the minimum residual in the optimal case, the ratio is less than or equal to 1 plus epsilon. I am talking about the minimum residual as measured using 2 norms, where Z is defined in 3. And this inequality, please understand, now x optimal is the original optimal, x tilde optimal is the optimal for the randomized version by downscaling. A, B, X, they are all not random, but multiplying by B makes it random. Therefore, X optimum is not random, but X tilde optimum is random. So, this residual A X tilde op minus B is a random variable. I am talking about the square of the norm of a random variable. I have to show that this square of the norm of the random variable is less than a positive quantity. That means there must be a probability associated with it. And what does it say? If Z is defined to be the optimum value of the residual, 9 will hold with a large probability. 9 will hold with large probability means what? There is a concentration involved in here. That means with a very high probability, I should be able to find an approximate solution, and the residual corresponding to the approximate solution, while random, due to concentration inequalities, the probability that it will be less than 1 plus epsilon times the optimal value is very high. So, that is what is called the confidence estimation, the quality of approximations that is involved in here. There is another way of expressing this result, or another related result. I should say another way of expressing another related result. Let kappa be a condition number of A, and we all know what is kappa is, which is the ratio of maximum singular value to the minimum singular value of A. Let gamma be a number in between 0 and 1, gamma be the fraction of the norm of B that lies in the column space of A. Let me talk about that now. I have AX are linear combinations of the columns of A, B is a vector in Rm. So, there are linear combinations of the n columns in the m dimensional space. B is a vector in Rm. The vector has an energy. It is represented by square of the length of the sum of the square of the length of the energy. The vector B can be resolved into a sum of 2 components. One is along the columns of A, along the span of A, that means the subspace spanned by the columns of A, that is an n-dimensional space, and that is perpendicular to that subspace. Is like any other standard orthogonal decomposition of a vector. Now, A is the matrix. You all know A admits an SVD. A admits an SVD. Now, let us come back to that. A admits an SVD. So, A is equal to U subscript A sigma A to the power half V A transpose. That is the SVD of A. You all know that. So, UA is the column vectors which are the eigenvectors of the larger Gaussian. VA are the column vectors which are eigenvectors of the smaller Gaussian. So, UA, VA, sigma A, you know what they are. It is this UA I am going to be utilizing here. UA transpose is a projection matrix onto the column space of A. So, the total energy in B, this is a fraction of the total energy in the numerator which lies along the span of A, and this ratio should always be less than or equal to 1. If it is equal to 1 means what? The entire B lies in the span of A, in which case the least square solution will be the actual solution that exists in X, for which Ax will be equal to B. But in general, in least square B may not lie. So, if gamma is the fraction of the energy in B that lies along the span of A, the rest of it perpendicular to that. So, UA is the orthogonal basis for the column space of A. So, in such a cases, what is that we can do? We can further quantify the properties of the relation between X optimal and X tilde optimum. What is X optimum? Is the true optimum for the original problem, Ax is equal to B. X tilde optimum, what is it? It is an optimum solution to the downscaled version of the problem, which is obtained by multiplying both sides by the downscaling matrix B. So, this is a solution to the randomized version, which can be solved in one of two ways. So, the difference between the optimal solution in the sense of 2 norm. So, this is the error in the solution, the 2 norm of the error in the solution. So, there are two ways of looking at it. One, you can think of it the error in the optimal estimates. I'm sorry. One thing you can talk about optimum value of the sum of squared errors, the residual space, or you can talk about the sum of the errors in the solution space. Please understand, the residual, they lie in the m-dimensional space. X lies in the n-dimensional space. So, X opt minus X tilde opt, this 2 norm of that is epsilon times kappa A times 1 over gamma square minus 1. What is gamma? Gamma is the ratio in 10. This constant multiplies the X optimum with respect to the 2 norm. So, if gamma is large, if the ultimate value of gamma is 1, so if gamma is 1, this upper bound becomes 0. That means X optimum is equal to X tilde optimum. If gamma is in between 0 and 1, there is an error. Please understand, that is essential. This brings to the essence of the square solution. And for these two results, so what are the two claims in here? The claim 9 and the claim 11. For these two results to hold good, there are some, nothing comes free. There are some conditions to be satisfied. They are called structural condition. And what is the structural condition? You remember the preconditioning matrix B. You remember UA, which is the eigenvectors of the larger of the two Gaussian, which are also called the left singular vectors of A. These are called the right singular vectors of A. So, this matrix, please understand, UA is a M by N matrix, BA is R by M matrix. So, this is R by n matrix. This matrix is rectangular, it has singular values. The square of the minimum singular value of this product matrix must be at least 1 over square root of 2. So, that is a structural condition that must be satisfied. There is another structural condition, U transpose B be perpendicular. What is B perpendicular? It is the component of B that does not lie in the range space, is perpendicular to the range space. So, in some measure this is the energy of B that is not in the range space, and that must be less than epsilon by 2 times sigma square. So, under the condition 11 and under the condition 12 and 13, we can readily prove 9 and 11, the claim 9 and 11, where gamma is defined to be a ratio in between 0 and 1, and again Z is the optimum value of the residual. So, I can quantify the optimal solution by looking at and comparing the actual residual to the optimal residual, or I can compare the quality by computing the optimal solution, the approximate solution, and the error in the approximate solution. So, these two ways of trying to fix it, and which is not unusual. In optimization problem, there is a minimizer and the minimum value of the function. I would like to be able to quantify the minimizer and the minimum value of the function, and that is exactly what is being done. Therefore, in summary, this is essentially a quick bonus which is coming out of our discussion of two approaches to randomized algorithm, one based on random selection, another based on random projection. And these two approaches can be combined together to have a uniform treatment, and that is the treatment of solving least square problems using randomized approach. There are lots of things need to be done. There is a good amount of theory, good dose of probability and matrix operations. Again, in summarizing, many of the authors, if you are going to be the first one to do something, you can use strong conditions. The subsequent others try to weaken the conditions. To prove inequality, sometimes using Frobenius norm may be easier, but we all know that the 2 norm is less than the Frobenius norm. So, one of the holy grail in numerical linear algebra is to be able to derive bounds based on 2 norms. So, if you look at the literature, first somebody may give a result in Frobenius norm, and then they will try to improve it to 2 norm, P norm, and each of these extensions tries to bring about the beauty of the underlying problem and the beauty of the mathematical arguments that are leading to a new look at the old solution, improved versions of the old solutions, and so on. So, with that, I believe I have given you a reasonably good understanding of what randomized algorithm in the context of least square methods is all about. Thank you.